Hello everyone, welcome to today's class. The topic that we are going to see today is modern symmetric key ciphers part 2. Modern block ciphers are all product ciphers, but they are divided into two classes. The first class, referred to as Feistel cipher, uses three types of components: self-invertible, invertible, and non-invertible components. The block cipher data encryption standard, which is known as DES, is a good example of Feistel cipher. The ciphers in the second class, known as non-Feistel ciphers, use only invertible components. The block cipher Advanced Encryption Standard, otherwise known as AES, is a good example of non-Feistel cipher. So let us move on to the Feistel ciphers. So a Feistel cipher combines all non-invertible elements in a unit and uses the same unit in the encryption and decryption algorithms. The question is how the encryption and decryption algorithms are inverses of each other if it has a non-invertible unit. So Feistel showed that they can be cancelled out. In the encryption, a non-invertible function fk accepts the key as the input. So in this diagram, you can see that P1 is the plain text which is XORed with a non-invertible unit fk. So this non-invertible unit, okay, which can be also termed as a non-invertible function, accepts k as its input. Afterwards, it is being XORed with P1 to produce C1. Now this C1 and C2, as you can see in decryption process, is the same. So now this C2 is being exclusive XORed with the non-invertible component, okay, and this non-invertible component also accepts the same key as its input, and afterwards, after it is being XORed, the output that it produces is P2. So we need to see if this P2 and P1 are same or not. So Feistel showed that despite of using this non-invertible component, the end product or the plain text will be the same. So we need to prove if P2 is equals to P1 or not. So we know that this C1 and this C2 are the same, right? So in encryption process, we can see that this C1 is being produced after being XORed with FK, right? So P1, this plus symbol indicates the XOR operation. So from now on, if this plus symbol is given, it will indicate the XOR operation. So this C1 equals to P1 plus or XOR of FK, right? Now let us see how this P2 is equals to P1. So this P2 is achieved in this decryption process, right? In this decryption process, we see that C2 is being XORed with FK, okay? Now this C2 is the same as C1, right? So C2 and C1 are equal. C1 and C2 are equal. So now this C1, how is this C1 being achieved? So this C1 is equals to P1 XOR with FK. So let us write this down here, P1 XOR with FK in place of C1. Now this Fk XOR with Fk. Now we know that if the same unit or the same element is XORed with itself, then it will fetch us the identity inverse, okay, which is this one. Okay. Now if P1 is XORed with the identity inverse, then we get the P1 itself. Okay, so this is the existence of our identity, right? So existence of identity. Yes, so that is how we can say that P2 is equals to P1. Okay, so P2 is equals to P1 proved. So Feistel showed that despite of using a non-invertible component, we can cancel the effect of this non-invertible component in our decryption process, and the end product that we will be getting, it will be the same as our plain text that we sent earlier. Now in the Feistel cipher, that was a very simple design. So here what we do is we want the input to the function to also be part of the plain text in the encryption and part of the ciphertext in the decryption. So we will shortly see how this is done. The key that we are using, okay, here, it can be used as the second input to the function. To achieve this goal, what we do is we divide the plain text and the ciphertext into two equal length, that is the left and right. So we call the left block L and the right block R. So the right block is being used as another input for this non-invertible function. So in this non-invertible function, what we are doing is we are using two inputs, the right part and the key. And then what is happening, this left part L1 is now being exclusive XOR with the non-invertible component, okay, and it is producing L2. So now what is happening is this L1 is being exclusive XORed with the non-invertible component, which accepts two inputs, the R1 and key, and then it produces this L2, and this R1 is directly transposed to this R2. And in the decryption process, we are seeing that the L3 is now equals to the L2, and this R2 is equals to this R3. Now, the L4 is being produced after this L3 is exclusive XORed with the non-invertible component, which accepts R3, this one, and the key K as its input. And then it produces the L4. And from this R3, we are seeing that it directly transposes to our R4. So we need to prove that this L4 is equals to L1 and this R4 is equals to R1. Okay. So we already know from this encryption and decryption process that this L2 is equals to L3, right? This L2 is equals to L3 and this R2 is equals to R3, right? Now we see in from our decryption process that this R4 is equals to this R3, right? And this R3 is equals to this R2, and this R2 is also equals to this R1. So basically the right hand side is doing nothing except for giving this as an input to our non-invertible component. It is just being transposed to its state, right? So this part is not affected at all, but the left hand side is affected. That is why we need to prove this L4 is equals to L1 as well. So let us see how it is being done. So firstly, what we see is in our encryption process, this L2 is achieved after L1 is exclusive XORed with this function, this non-invertible component, which accepts R1 and K as our input. Okay. So in order to prove L4 equals to L1, we see that L4 is being achieved through this L3, which is being exclusive XORed with the non-invertible component, this one, right, which accepts the R3 and K as their input. Now we know that this R3, okay, this is equals to the R2, right? Yes. So this R3 is equals to this R2, and this L3, it is equals to the L2. So L3 is equals to L2. That is why we can write L2 instead of L3, and instead of R3, we can write R2. Okay. So now you can see here in our encryption process, we got that L2 is equals to L1 XOR of FR1 and K, right? So this is what we got in our encryption process. So we can write this one instead of this one, right? So we have done exactly that. We have written L1 plus the non-invertible component, okay, plus this remaining thing. Now here you can see this R2 is being changed to R1 because we know that R2 is equals to R1 as well, right? So what we are getting now, we see that we are getting two units, okay, and they are being XORed with itself. So this will give us the identity inverse, right? So yeah, this is giving us the identity inverse. So let me erase this. Yeah, so this is giving us the identity inverse. Now if we XOR something with the identity inverse value or the identity value, then we get that value as well. We get only that value. So we are getting this L1, which is the identity existence, right? So this is how we are proving that L4 is equals to L1 and R4 is equals to R1. Now Feistel further improved on this design and made a final design because there was a flaw in the previous design. Now this flaw, as we can see that in the previous design, the right side text doesn't change, right? So since the right side text doesn't change, what happened is Feistel wanted to make the right hand side change as well. Okay, so in the previous design, this R1 was equals to the R2, which was equals to R3, and which was eventually equals to the R4. So Feistel wanted to change that, and in order to change that, Feistel introduced the addition of swapper and rounds. Okay, so what is happening here is the same thing that was done before is being implemented, just the swapper was introduced, and this swapper was introduced so that this R1 and L1 could change their position. Okay, now what is happening here, let us see in detail. So here this L1 is being exclusive XORed with the non-invertible component which accepts R1 and K1 as their input, and this is producing R2. And this R1 is being fed as an input to this non-invertible unit, and later on it is being changed to L2. Now again in this L2 it is being exclusive XORed with the non-invertible component which accepts R2 and K2 as their input and produces R3. And this swapper, you can see this position is being changed to R3, right? And this R2 is being directly transposed to L3. Now this L3 and R3 are equals to L4 and R4, okay? And this L4 is now being accepted as the input of this non-invertible component, and the K2 is also being accepted here, right? So in this non-invertible component in our decryption phase, we will be accepting L4 and K2. So before going further into this decryption process, you can see in the encryption process, firstly we implemented the mixture and then the swapper. But since our decryption needs to be inverse of this encryption process, so the first process that we will be do is the swapper, okay? And then the mixture. So this will be our round one. So our round will be beginning with a swapper first. Whereas in our encryption process, it started with a mixture, right? For its round. So what is happening now then? So this L4 is, and this K2 with the non-invertible unit is now being XORed with R4, and it is producing L5. And this L4 is being directly transposed to our R5, okay? So this L4, R5, they are equal, okay? And the L3, R4, they are also equal as well. So what we can see is this L5 and K1, right? They're being used as the non-invertible components, okay, in the non-invertible function. And this R5 is being XORed with this non-invertible component, okay? And it produces L6. And this L5 is being directly transposed to R6. So what we need to do is we need to prove that in this final design, the L6 is equals to this L1 and this R1 is equals to this R6, right? So Feistel showed through this design, in spite of using a non-invertible component, we can cancel the effect of those non-invertible components and yet achieve the result that we want or the result that we intend. So we have to prove that this L6 is equals to this L1 and this R6 is equals to this R1. So we already know that this L3 and L4 are equal and this R3 and R4 are equal as well. But since it's a long procedure to prove, let us start from this middle text, okay? So we will be now proving L5 equals to L2 and R5 equals to R2 so that we can eventually prove the things that we require. So here you can see that L5, as we started from the middle text, is equals to this R4, which is being XORed with the non-invertible function component F, L4 and K2. So we have written this here, right? So this is written here. Now this R4, we know that this R4 is equals to this R3. Similarly, this L4 is equals to this L3, right? So we are writing this here. So this R4 is equals to the R3 and this L4 is equals to the L3, right? Then what we are writing, this R3, right? This R3, how did we obtain this R3? So this R3 was obtained after we have performed the exclusive OR operation, including L2 and this function component, right? This non-invertible component. So L2 XOR of F R2 K2 gave us R3. So that is why instead of R3, we are writing L2 XOR of F R2 and K2. Okay, and then here what we are writing is instead of L3, okay, instead of L3, so this is our L3, right? So this L3 has been directly transposed from R2. So it means that they are equal to each other. So instead of L3, we can write R2 as well. Okay, so now we can see that this thing that is being XORed, they are the same thing, right? So here we can use the identity inverse. So if we use the identity inverse, then this too will fetch us this result, which is the identity inverse. Now, if an element or unit is being XORed with the identity element, then that operation will fetch us the unit. So this is the existence of identity, right? So we are getting L2, okay? So this is how we can get L5 is equals to L2. So L5 is equals to L2, right? We have proven that. Now, this R5, okay, this is equals to this L4, right? So this R5 is equals to this L4, and then this L4 is equals to this L3, and this L3 is equals to the R2. So R5 L4, L3, R2. So that is how we can prove R5 is equals to R2 as well. Now, since we have proven this one, we can go for the L6 is equals to L1 or not. So you can see here that L6 is being achieved after R5 is being XORed with L5 and K1. Okay, so that is what we have written here. So L6 is equals to R5 XOR of the function element L5 and K1, right? Now we see that R5, okay, R5 is R2, right? So we can write that R2 here, and L5 is L2. So we write that instead of this, right? So R2 and L2, we have written it here, right? Now this R2, so how is this R2 being achieved, right? So R2 is being achieved after we have performed the XOR operation with L1 and this function element, right? And this non-invertible element, FR1K1. So we can write that here. So instead of R2, what we can write? We can write L1 plus FR1K1. Okay, since we have achieved R2 through the XOR function of L1 and the FR1K1. Okay, so after this, what we can do? We can write this L5, right? You see this L5? So L5 is equals to L2. So we can write L2 here, right? We can, instead of this L5, we can write L2. Now this L2 is equals to this R1. So L5 is equals to L2, but this L2 is equals to the R1. So we can write R1 instead of L5 here. So now from this, you can see there are the same elements. So we can use the identity inverse to cancel them out, and we get something like this. And when we use the identity element with another element, we get that element from which we use the identity element, right? So that is what we get here, L1. So here you can see L6 is equals to L1, which further says that L6 is equals to L1, which we have proven. Okay, and now here R6 is equals to L5, right? This R6 is equals to L5, as we are directly transposing this R6 from L5. So this L5 is equals to L2 that we have proven over here, right? Now this L5 is equals to L2, and this L2 is being directly transposed from R1. So that is how we can write R1. So this is how R6 equals to R1 as well. So this is how we can say that the encryption and decryption process in our Feistel ciphers, they are inverse of each other. The non-invertible component doesn't affect it. Rather, it cancels each other, okay? Since we are using their inverses. Now moving on to the data encryption standard, which is a modern block Feistel cipher. So as you can see in this diagram, what is happening is at the encryption side, this data encryption standard or DES takes a 64-bit plain text and it creates a 64-bit ciphertext. Okay, it takes a 64-bit plain text and it creates a 64-bit ciphertext. Similarly, in the decryption side, the data encryption standard or DES takes a 64-bit ciphertext and it creates a 64-bit plain text. So the same 56-bit cipher key is used for both the encryption and decryption. Now let us see how this DES is structured, okay, the structure of DES. So here you can see the encryption process is made up of two permutation boxes or P boxes, which we call initial and final permutation. So here you can see in this DES structure that after this 64-bit plaintext is entered through the system, it will go through up initial permutation, and in the end there is a final permutation. Okay, between this initial and final permutation there is a total of 16 rounds, okay, which are also known as 16 Feistel rounds. So each round uses a different 48-bit round key generated from the cipher key according to a predefined algorithm. So this 56-bit cipher key, it is fed to this round key generator, which produces a 48-bit key, okay, for each of the round. Now let us take a look at what this initial permutation and final permutation are. So each of this permutation takes a 64-bit input and permutates them according to a predefined rule. So these permutations are keyless straight permutation that are inverse of each other. For example, in the initial permutation, the 58-bit in the input becomes the first bit in the output. So as you can see here, the 58-bit, okay, in the input is converted to the first bit in the output. Similarly, in the final permutation, the first bit in the input becomes the 58th bit in the output. So the first bit in here becomes the 58th bit in the output. So essentially, they do nothing, and it is not clear why they are included in DES. but experts think that they were implemented to thwart a software simulation. Now let us move on to the next part, which is the DES rounds. Okay, the 16 rounds that we have mentioned earlier. So in this DES round, what happens is it takes Li-1 and Ri-1 from the previous round or initial permutation box. So this 32 bits for each round, they are coming from the previous round. All right. And this 32 bits will go to the next round and it will also produce 32 bits. So each of this round, the beginning, they are coming from the previous round and they're producing an output, and this output will also be used in the next round as well. So as there are 16 rounds in total, so for the first round, it will take its 2 bits from the initial permutation, and in the last round, the 32 bits will be fed into the final permutation box. So each round has 2 cipher elements, okay? So we can see the mixture and swapper that we have previously seen for our product cipher as well. They are also used here, the mixer and the swapper. So each of this element, as we have already seen, they are invertible, right? The swapper is obviously invertible. It swaps the left half of the text with the right half. The mixture is invertible because of the XOR operation. And the non-invertible elements that are collected inside the function, this function, they basically cancel each other out in the encryption and decryption processes. Okay, now let us see how this function is implemented. Okay, how is this done in our DES? So this is the DES function. Okay, this is the overall overview of the DES function. So the heart of DES is basically the DES function. The DES function, what it does is it applies a 48-bit key to the rightmost bits, okay, that we have seen earlier. There are two parts, left and right part. So this 48-bit key is applied to the rightmost part bits, just like our product cipher. And what is happening here, it will produce an output of 32 bits as well. So the input is 32 bits and the output will be of 32 bits, but the key that we are using, it will be of 48 bits. So let us see how this is being done. So this function is made up of 4 sections. The first one is the expansion P box, then we have the XOR, then we have the S boxes, okay, and then we have a straight P box. So the expansion P box produces an output of 48 bits, which undergoes the XOR operation to give an output of 48 bits. Now here you can see in this 32 bits, the expansion P box, basically what it does is it produces an output of 48 bits, okay? So we will see soon how this is done. But for now, just know that this will produce a 48-bit output. Then this 48-bit output is being XORed with the key, K1 key that is being generated, right? Now, after being XORed, okay, these 48 bits are now grouped into 6 bits, okay, 6 bits of 8 S boxes. So they are grouped into 6 bits of 8 S boxes. So how many S boxes are here? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 X boxes, right? So these 48 bits are grouped into 6 bits of 8 S boxes, right? And they produces an output of 32 bits. So remember this, the X box are producing an output of 32 bits. After this, this 32 bits is now applied to a straight P box, which is responsible for generating this 32 bits as well. Okay, so this is just basically transposing or reordering the position after the X box has produced an output. Okay, now let us see how this expansion P box is working. So the functionality of this expansion P box is shown here, as you can see in this diagram. So the 32-bit input, okay, that we are feeding into this expansion P box, it is now being divided into 8 4-bit sections. So how many? 1, 2, 3, 4, 5, 6, 7, 8. So it is being divided into 8 4-bit sections. Now each 4-bit section is then expanded to 6 bits in its output. So as you can see, this 4-bit section is expanded into 6 bits in the output, right? So that is how it can produce an output of 48 bits. Now, what is the working principle or the methodology that it produces 6 bit? So we see that for each section, the input bits 1, 2, 3, and 4 are copied to output bits 2, 3, 4, and 5 respectively. So you see here the input bits 1, 2, 3, and 4 are copied to the output bits 2, 3, 4, and 5 respectively. Now, where is this output bit 1 and output bit 6 coming from? So output bit 1 comes from bit 4 of the previous section, and output bit 6 comes from bit 1 of the next section. So you see the output bit 6, this is the output bit 6, it is coming from the input bit 1 of the next section, and the output bit 1, okay, it is coming from the input bit 4 of the previous section. So in this manner, basically the expansion box is being formed. One thing that you need to notice, the first output bit is coming from bit 32. So if sections 1 and 8 can be considered as adjacent sections, so we can see that this output bit 1 is coming from bit 32, and this output bit 32, it is coming from bit 1 of the input, right? So basically this is how the expansion P box works. Now moving on to the S box of our des function. So you can see here we have the X box, right? So you can see there are a group of 8 X boxes here. So these X boxes are responsible for making the confusion. Now this des uses 8 S boxes, each with a 6-bit input and a 4-bit output. So that is how this 48-bit that is being fed into this X box will produce a 32-bit output. Now the 48-bit data chunk from the second operation is divided into 8 6-bit chunks. You can see how many? 8. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 X boxes, and in each of these X boxes 6-bit chunks are being fed. Okay, so how many? 1, 2, 3, 4, 5, 6. So there are 8 X boxes, and in each of these X boxes 6 bits of data or input will be given. Okay, now the result of each box is a 4-bit chunk. When these are combined, the result is a 32-bit text. So from each of the S box, we will get a 4-bit output. How much? 4-bit output from each of the X boxes. So after getting a 4-bit output, so we have 8 X boxes. So this 4-bit output will give us a total of 32-bit output, right? After this 32 bits is now applied to a straight P box, which is responsible for generating this 32 bits as well. Okay, so this is just basically transposing or reordering the position after the Xbox has produced an output. So as you can see in this des function, we are getting an input of 32 bits and getting an output of 32 bits. Then this 32 bit is being exclusive OR. Okay, it is being exclusive OR with the left hand side part. Okay, the left hand side 32 bits that we have seen in our structure. So after this 32 bits is coming out, it will be exclusive OR with the left hand side part, and this left hand side part then will eventually swap its value, and then it will be going to the next round as well. Thank you. This will be all for today's class. Hope you have understood and enjoyed the class as well.